There we go. And we're back live. Make sure that microphone works. I believe it does. Excellent. So this is the last class period. I'm going to see you guys for a bit. When am I going to see you next? I'm going to see you on the 12th. Yeah. So it's like a week. It's like almost, I don't even know how long that is really. Week and a half really, but whatever. But yeah, I won't see you guys until April 12th. When we come back on April 12th, of course, we will recap some of the stuff that we've been learning with Euler paths and circuits. And we'll continue and see what else we can kind of add to our arsenal of things, because I do have a ton of stuff that I would love to get to in the remaining time of the school year. In regards to today, I have a couple. I have a couple challenge games for you that I want you to kind of try. I have a video that's going to explain the first challenge in a few moments once I get this thing loaded. I'm just stalling for people to get into the live chat. And yes, if you're in the live chat, please leave me a comment. That would be wonderful. For some reason, it says unable to connect to chat. I really hope that's not going to be an issue. If it is an issue, I do have an alternate plan. So for those of you in the live chat, stay tuned if that live chat doesn't actually work out the way that I hope it will. But we'll see what happens. Anyway, so I do have a video introducing the first challenge. Then I would like to just get a little bit of practice in regards to what we were doing with Eulerizing the other day. I do have a practice quizzes lined up that I would like to give it a try at some point. But again, I'll let you know when we do that. And then I have a weird kind of star-making game for you at the end. I don't know. Question. When you were in elementary school, what kinds of stars would you guys draw? If you were in elementary school and you were told, "Hey, draw a star on paper," what would you exactly draw? Exactly, though, right? Yeah, you would normally do something like like that, right? Yes, I do have a game for the end of class that's going to help you make. Well, not that you want to do that, but that's going to help you make every size star you could ever imagine. But again, we'll get to that. We'll get to that when the time is appropriate. Again, for those of you in the live chat, I really, really hope that this is working out. It says unable to connect. Is anyone able to hear me? Question mark. I really hope that works. If it doesn't, well, like I said, I do have a backup plan. But in the meantime, I want to start off with a little game. I want to start off with a video that is going to describe the first game that you are going to be challenged with this morning. While I try to figure out this whole thing with the chat, I really don't know what's going on with it today. So let me drag this thing over. Chapow. Make that thing big. Shatu. There we go. And let's see what this guy has to say.
Hello everybody, I have a puzzle for you, and perhaps this is one you can try out on your friends and family. Look at this picture. Now the puzzle is this. Can you draw a continuous curve without taking your pen off the paper that crosses each line once, and once only? So,
now hold on, I'm going to rewind that just to show that challenge one more time. It seems like a very simple challenge. That drawing is just like 5 rectangles or 5 kind of quadrilaterals kind of floating around, but he does have specific rules for what he's referring to. So let me go back to the instructions, and then I'll kind of clarify what he's saying, and then he's going to show an example.
Friends and family, look at this picture. Now the puzzle is this. Can you draw a continuous curve without taking your pen off the paper that crosses each line once, and once only? So it might look something like this. Okay, let's say I start over here.
Pause. There we go. No, back up. So just to clarify what he's about to kind of go through, what he's referring to is something like this. There is a line on this shape from here to here. And if he goes through this right here, then he is done with that line. And the rules of his game is he's going to try and go through every single side on the shape, inside and outside, without lifting his pen once. So, for example, this right here, from here to here, counts as a side. From here to here, counts as a separate side, to keep that in mind, the line that you would have to go through. Fun noises, like something like that. So far, I've gone through 1, 2, 3, 4, 5, 6. I've gone through 6 sides. Now, he's going to give it a try. He's going to go in a slightly different direction. But let's see how this actually works out.
So it might look something like this. Okay, let's say I start over here. I come into the box and I cross that line. And I go up through the top. I go over. I come back down, cross that line, go out of the picture, come back in, go through there. So I cross this line, through here, down through this line. Now it's important to remember these two halves of this line count as 2 different lines. So I can go up through here, that is allowed. And then I come back down, round into this box and right. Now I have to stop there. So if I go down again, I cross this line twice, which is not allowed. So I nearly did it, but it didn't quite work. Now the question is, can you do it? If you don't want to know the solution, I suggest you pause the video now because I'm going to give you the solution in a second.
Pause. There we go. So I'm just going to rewind one more time just to kind of show what this guy did. Hold on. Ooh, come on. Where's my... There it is.
Only. So
here we go.
It might look something like this. Okay, let's say I start over here. I come into the box and I cross that line. And I go up through the top. I go over. I come back down, cross that line, go out of the picture, come back in, go through there. So I cross this line, through here, down through this line. Now it's important to remember these two halves of this line count as 2 different lines. So I can go up through here, that is allowed. And then I come back down, round into this box and right. Now I have to stop there. So if I go down again, I cross this line twice, which is not allowed. So I nearly did it, but it didn't quite work. Now the question is, can you do it? If you don't want to know the solution, I suggest you pause the video now because I'm going to give you the solution in a second.
Pause. So, just quick comment for those in the chat. Again, I'm not sure what's going on with the chat window. This thing is clearly live streaming and clearly recording things that are going on. I can see the thing through my phone on a separate account. So for those in the live chat, I just left a post in the Google Classroom for you to comment on in order for us to get proper attendance for the day, just in case you are unable to comment in that chat. So I want you guys to try this. I do want you guys to try this. I want a few minutes just to see what you can do. It's actually fairly simple to recreate this image. If I can find the right marker here. That's not, where's my black marker? I had a better marker. I'll find it somewhere. Anyway, but it's not that hard to recreate this particular image. Here we go. Because it is just 5 rectangles, but you can just make like one rectangle, cut it right there, cut it right there, cut it right there, cut it right there. Boom, I got it. And then you can try the little challenge. So take a couple minutes, draw that thing out, see what you can do. See if you can follow his rules and complete the game. And then he's going to talk about the solution. Actually, well, I'm going to talk about my solution, but we'll deal with that. I want to see what you do. Let's see here. Still, that live chat is messing up on me. What's going on with this thing? I know. Oh, the chat is working. Is the chat working now? Yes, I see you here. I don't know why I thought the chat was not working for some reason. Oh, I'm going to leave that post up on Google Classroom. When we do eventually go over the solution, I am going to put the solution into our notes simply because I love what this problem turns into. Yes. No, get down there. There we go. Then I get this. Then I duplicate there. Come on. Where are you? There you go. Zoom out a little there. What are you thinking?
I'm missing mine alone.
Is there a particular strategy that you think might be helpful?
Maybe.
Oh, each side, inside and out. Only once per side. Oh, excuse me. Painful. Okay. You're unable to complete said challenge, correct? Do you know why? Okay. Now that's the key here. This is where it relates to everything that we're doing. So just for the sake of argument, obviously you already have the pages out for your notebook, but I'm going to remind everyone in the chat here to have those notebooks out and open, because this is the path game that I am showing you. Now I'm going to go up to the board and I'm going to give this game a couple of tries. Make sure you're copying the little note that I had right here. I meant to word this differently, but it's basically you have to go through each side of the shape, inside and outside, without lifting your pen, and you can only go through each side once. So you could do something like, okay, going through each side exactly once. Maybe I'll just stick to over here, going through each side exactly once. This counts as a side right here, as the guy said. But if I go up there, I'm stuck. So maybe I'll come through there last. So I'll go through there. I'll go through there. I'll go through there. I'll go through there. There. I got so stinking close because now there are two sides left for me to go through, but if I go through one of them, I'm completely and utterly stuck. That's the closest I can get. Unfortunately, there's no way of doing this. There is absolutely no way of doing this problem. This problem is deemed impossible. But the question is why? Why is it deemed impossible? Why is this problem not able to be completed as is? And I will give you the reason. You can convert this game into a graph that we have done using Euler paths and circuits. You absolutely can. See, because every time you draw a line through a side, those are considered the edges. Those are considered the edges. So for example, and I'm going to draw this now, obviously you have pencil. I'm going to do this in red just to show you the distinguishing markers here. But at some point I would draw a line through that side, 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 and that side. At some point, I would have all of these edges just kind of floating around. Maybe I can get like a red. Oh, here we maybe. I was trying to get a red marker to kind of show it a little bit better. Maybe I'll do it like that. Might be a little bit easier. Yeah, it might be a little easier to see for those in the chat, obviously. But these would represent all of my edges. And wherever these edges kind of come together forms a vertice. Wherever these edges come together form a vertice. So for example, if they're going to come together right in the middle here, and here, and here, and here, and here, they would form vertices. Now, I don't know what the outside of the graph is doing. I have no idea what the outside of the graph is doing. It doesn't matter to me what the outside of the graph is doing. What matters to me at the moment is what the heck is going on the inside. Because this game can be redrawn. It can be redrawn as an Euler graph. So let me put a little note down here. This game, and I'm going to show you how you can redraw it, can be redrawn, I can spell today, as an Euler graph. And I want to show you how we can do that. Now, like I said, every time you actually go through one of the sides could be an edge. Here, 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 and here. There's a whole bunch of edges floating around. But now when these edges connect, it's like a node is what they call it, or a vertice or something along those lines. And there's a reason why you cannot complete the Euler path if it is so called. The reason why I call it an Euler path is because the idea is that you are going to go through each side exactly once, meaning you are only going to go on each edge exactly once, which are the rules of taking an Euler path. It doesn't matter where you start and finish. I mean, you could start and finish in the same location. That would be an Euler circuit. But an Euler path would just be hitting every edge exactly once. So here's how we would redraw it. Here's how we would redraw it. Instead of the image that I had above, I'm going to draw these 5 vertices right here. And I'm going to connect them in the following way. Now, some of these vertices have edges coming off of them. And I would like you to obviously draw this into your notes as well. But some of these vertices have edges coming off of them because they connect somewhere else. I don't know exactly where else they connect, but it doesn't matter where else they connect. Because what matters, I'll put this off to the side, what matters is the degree of each vertex. What matters is the degree of each vertex. That we got going on right there. Just for the sake of argument, look at the one that I'm pointing to right there. According to our game, what is the degree of that vertex?
Just the one you're pointing to?
Oh, yeah.
5.
Yeah. What about this one?
5.
Yeah, and what about this one?
5.
Now that's the key. I don't care about the other two. I care about those three. And here's why. Actually, yeah, I'll put it here and here and here. All three have degree 5. All three have degree 5. In order to get an Euler circuit, we need all even degrees. This is what we wrote down the other day. In order to get an Euler circuit, you need all even degrees, all of them. But we have 3 odd ones right there. In order to get an Euler path, we need exactly 2 odd degrees. We need 2 odd degrees. Unfortunately, we have 3. And if you have 3 odd degrees, then neither one is possible. You can't do it. These 2 definitions that I gave you the other day for an Euler circuit and for an Euler path prove that this game that this guy is proposing is absolutely impossible. And what he's basically suggesting, and I'll show you the rest of the video, what he's basically suggesting in the game is, hey, fool your friends and family. Have them try this game. Explain to them the rules, and then let them have a try, and just watch as they just try until they give up. That kind of sounds mean to me, which is why I only let you go for a couple of minutes. I don't know. How many times did you try? That's what I'm saying. Like, I'm not gonna push you farther than that. Well, let's just see what the rest of this video this guy says in here. Hold on.
So if you want to try it, do pause, stop, or do something like that, because I can tell you that this is impossible. But I want to know why it's impossible. Let me show you how to prove it. Here's that picture again. Now what we want to do is we want to cross each line once and once only. So let's draw that in. So I want to cross this line like that. I want to cross this line. And I want to cross all these lines. And I want to cross them each once. So this is exactly what I want to do. Now, to finish this off, really it should just be a case of joining up the dots. And so I might come into this box and then I'll go up through the top like that. Let me add just one more thing. Let's say every time I enter a box, I make a detour to the center. So let me draw that in. I'm going to draw in the center points. So there, 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 and there. Okay, let's join up the dots now. If we do, this is what we'll get. We'll get a picture that looks like this. Now this is a diagram that tells us everything that we can do. Now I haven't connected the curve outside the picture, but certainly inside the picture, this tells us everything we can do. So if I could come into the box here and I go to the center, I could go up through the top, or I could come in and go to the center and I could go down this way, or I could come into the center and I could keep going and cross this line like that, and then I could go up. This really tells us everything that we can do. Now, every time I enter the center of a box, I leave it again. So lines into the center come in pairs. We should have an even number of lines at each center point. There are two exceptions to this, and they are if the center point is the beginning point or the end point. In that case...
Now, what he's actually describing when he says there are two exceptions, he says if the center point is the beginning or the end. He's referring to the odd vertices one for an Euler path. For an Euler path, if you had the two odd vertices, the rule of thumb is you start at one of the odd vertices and you finish at the other odd vertice.
We may have an odd number of lines. So we can have at most 2 points with an odd number of lines. But here, in this diagram, we can see that we have 3 center points with an odd number of lines. And that's why it's impossible to draw. This idea has a proper name, and it's called an Euler's trail. The idea of drawing a curve such that each point has an even number of lines, perhaps except at the beginning or at the end. That's called an Euler's trail. And that is how you do it. So, as usual, if you have been...
Euler's trail, I mean, it's just the same thing that we've been doing with Euler paths and circuits. I don't know why. I don't know if it's an English thing to call it an Euler trail, but whatever. Okay. Here's what I want to do. I would like to get a little practice in. I want to see, with the information that we've done so far, I want to see how well we've done, and I want to know what we need to work on. So I do have this quizzes lined up. Now, this is just a practice. This is just a practice quizzes. But I want to see where we are and how we're doing with the limited information that we've gotten so far. Now, obviously, there's still some things that we need to do. There's still some gaps that we need to fill in regards to this information. There are other paths and circuits that we can talk about. But this is talking about some of the initial pieces of information that we got to knock out. There is one word in this thing that they use. They use the word at some point valence. They use the word valence. The valence is the degree. Valence is the degree of the vertex. That's all that it really is. They just use the fancy word like valence. So I don't really know what they're going to do with that. I should turn down the volume. I'm going to type that thing into the chat as well, just in case, even though I think that you guys can see that. 567 111. 567 111. Just to give that thing a shot. You know, fun fact, last year when I taught this class, before COVID, I only had 7 kids enrolled in it. And then once COVID hit and we were all at home, I was literally down to like 3 or 4 kids. because the rest of them just kind of like, oh, the age of COVID that we live in. All right, I'm going to get this thing started. Still an opportunity to join in with that code. That code is still live at the top. right. Let's see. Sort by accuracy. How many redemptions did you use? Just one? Okay. Okay. So this graph will have an Euler path. Let's see. Boom. I know it's, yeah. I mean, obviously you know what the correct answer is now, but just what I would look at if I were doing a problem like this, I would see that this automatically has a degree of 3. This has a degree of 3. And this has a degree of 3. I wouldn't even bother looking at the rest of it. Because since I found 3 odd degrees, I know it can't have a path. I'm sorry, let me rephrase. I know it can't have an Euler path. You can have a path, but an Euler path would be hitting every edge exactly once. Having that special designation of being Euler is what causes it to do so. Let's see this one. Which of the graphs below have Euler circuits? Circuits imply to me that I got to have even everywhere. So you said 2 only. I'm assuming because it was 4, 4, 4, and 4. This one, 2, 4, 4, 4, 4, 4, and 2. Yeah. So since it's all even, it's got to be. It's got to be that. Were the pictures large enough to? Okay, just making sure, because sometimes they're like, sometimes I don't know, the formatting gets messed up, you know. But since that one had all even degrees, then yeah, absolutely, they're both Euler circuits. Let's see this one. Circuits start and stop. They got to be at the same vertex. The whole idea of a circuit is that it completes that circuit. You ever rewire a lamp? No? I had to rewire a lamp a few years ago for the first time, and I had to learn how to do it, and I was scared out of my mind. But I was successful because I watched YouTube. But the general idea of AC-DC current, when you plug something into the wall, there are typically, well, on these walls right here, there are 3 holes? Do you know what they do? Well, what each individual thing does. Okay. The circular one is a ground, just to try and prevent, people from getting electrocuted. But the other 2, one of them electricity comes in and the other electricity goes out. And it's just that general idea of like continually moving AC-DC current. When you rewire the lamp, if you've ever seen like a cord for something, there's usually like 2 little wires or something. And again, same thing, electricity is moving in one direction in the one wire and the other direction in the other, but it's got to be one continuous flow. So if I turn on a lamp, that lamp is the beginning and the end of that current running because all of that electricity is running through the light bulb. It has to start and stop in the same location. But then the second that I break that current by turning off the lamp, then obviously the electricity is not flowing and the light bulb goes dark. Science! Anyway, back to this. Do you guys learn that in science? All right. There was a movie a couple years ago called The Current Wars. You ever hear about that? It was just basically, I want to say it was Edison, was a ruthless businessman, and he basically tried to paint his competitors, especially Tesla, as a dangerous individual who didn't know what he was doing. And as a result, like the smear campaign worked, and for 100 years, nobody touched Tesla coils because they thought they were dangerous. And now all of a sudden, we're back to Tesla. Okay. Weird, Tesla. So do you remember which one you had to do the redemption on? Yeah, I got you. Yeah. We never talked about connected or not, but literally, like, connected is just like, is it literally connected? Like, clearly this one's not. No, where's the other one? Is this it?
Yeah.
Connected because one can get from one vertex to any other vertex in the graph. Yeah, it's just basically think of it literally like everything is connected to each other. There's nothing kind of dangling off, floating in space. Weird. Exit that. Okay. Nice. Get rid of that. All right, so I do have two things. I could have two things. Do you know the story, or not the story, but the riddle? And people have done different things with it, but this one I believe has to do with a sheep, a wolf, and a cabbage, or something like that, and getting them across a river. Do you know that riddle? Oh, snap. Hold on. Okay, hold on. Wolf, sheep, cabbage, riddle. This one. I want to say it's this guy. I'm not going to play the whole video. I got to get past the advertisements.
When Leonard Euler.
Hey there, my name is Xavier, and I've got an interesting puzzle for
you can't see it. You can't see it because I never flipped the
Imagine
thing
you're
over. What am I doing here? Flip the thing over. There we go.
farmer, and on the local market, you bought a sheep, a wolf, and a cabbage. Kind of a strange situation, but just go with it. On your way back home, you have to cross a river with your boat. However, there's a catch. The boat is only big enough to carry you plus one other item. And to complicate matters even further, you can't leave the wolf alone with the sheep because the wolf will eat the sheep. Likewise, the sheep will eat the cabbage if you leave them unattended. This is called a river crossing puzzle, a type of transportation puzzle, and it's a relatively simple one. You can probably solve it with a minute or two of thinking. So go ahead, pause this video, I'll wait right here.
Okay. You never heard this puzzle before?
No.
Oh my gosh. It's amazing. This is one of the classic logic puzzle things. But the thing is, what this guy does is he uses what we've been doing with graph theory in order to kind of get this thing solved. So the general idea is there is a river that you have to cross. And on one side of that river is you, a wolf, a sheep, and cabbage. And you have to get all three across the river. However, you have a small raft. I'll just draw like a little boat right here. There we go. You have a small craft, a small boat that can only fit two things at a time. You and one of those three objects, or the wolf, the sheep, or the cabbage. You have to get all three across the river. However, if you leave the wolf alone with the sheep, the wolf will eat the sheep. If you're there with the wolf and the sheep, the wolf will not eat them. If you take the wolf across and leave the sheep and cabbage by themselves, the sheep will eat the cabbage. If you leave the wolf with the cabbage, nothing will happen. The idea is, okay, how do you safely get all three across the river? Yeah, you can go back and forth as many times as you want, but you got to be in the boat. So let's see, hold on. If you take the sheep first, then it's you and the sheep. Okay, now what? Okay, so then you go back over here, and then you and the wolf. So then you and the wolf are now over here. Tell me what you're thinking. By themselves. They can't be there by themselves, otherwise the wolf will eat the sheep. is where people kind of get stuck, right? Let's try again. We'll go back. Hold on. You, wolf, sheep. We'll go back to the beginning. Do you want to start it the same way or try it differently?
Just one at a time?
Yeah, you and one of the three are in the boat going across. You can't take more than one. You can't take two of them and put them in the boat and shove it across, because then you don't have a boat. You need to get all three safely across the river.
You and cabbage first.
If you take you and the cabbage, the wolf will eat the sheep.
Okay. You and the wolf.
Then the sheep will eat the cabbage. Well, let's see. We'll take the sheep across. So now you and the sheep, you can leave the sheep over there, and you come back over here. There's you. If you stare at the word sheep long enough, it looks misspelled. Anyway, what do I do next? You could leave it there. You got to get all three across. Now your sheep's just sitting there. It is possible. Well, now what this guy is going to go into is not the details of how it works. I'm going to show you how it works in a moment. But what he's going to go into the details of is the graph theory, because inspired by Euler paths and circuits, he's going to go through the graph theory as to how to do this problem. But let's just see what happens. You and the wolf can go across like that. But then you and the sheep go back. Now, the sheep will not eat the cabbage as long as you are there, correct? Then you and the cabbage go across. Now, the cabbage will be safe. Exactly. And then you and the sheep can get over there safely. Yeah. You never thought about going back with something. Yeah. It's a little bit of thinking outside the box. But now let's see what this guy says. Because what he is going to do is he is going to map this whole thing out.
It probably didn't take you too long for you to realize that you have to take the sheep across first, because the wolf won't eat the cabbage. Then you go back to fetch the wolf. But since you can't leave these two unattended, you take the sheep back across the river. Then you take the cabbage across because the wolf won't eat it, and finally you go back to fetch the sheep. Ta-da! All of your purchases have now made it safely across the river. Because this puzzle is so easy, we can solve it by using trial and error. But how do we know that the solution we found is the only one? And how do we solve more complicated puzzles? Our guesswork isn't very scalable and becomes even harder when we add more variables to constrain the puzzle. So instead, we can use something called graph theory, a field in mathematics which studies graphs. A graph is a representation of elements that are connected with lines. Each element is called a node, and the connection between them are called edges. Now let's solve our puzzle by using graph theory. We'll start by writing down all the valid states for our puzzle. The starting state is simple. The farmer, sheep, cabbage, wolf are all on one side of the river. The desired end state is also easy. All of them have to be on the other side of the river. From there, we can, for instance, start by transporting the sheep across the river. We can do that because the wolf won't eat the cabbage, and we can travel back as well because the sheep is fine by itself. The inverse of these two states is also valid, so we can write those down as well. Now let's go back to state 2. From here, we can transport the cabbage across and leave the wolf alone. Just like before, the inverse is valid as well. But now we have a problem. We can't leave the sheep and cabbage alone, so we have to take one of them back with us. If we take the cabbage back with us, we end up in state 3. So let's take the sheep back across instead. And once again, the opposite situation is valid as well. And that's it. That leaves us with 10 valid states for our puzzle. Now we can start constructing our graph. We'll start by creating a node for each of the possible states. and then we can connect two nodes if we can move between these states. So our first node is number 1, where everyone is on one side of the river. From there, we can only go to state 2, because we can't leave the wolf with the sheep or the cabbage with the sheep. Then we can only go to state number 3, where the farmer goes back across the river. But now he faces a choice. He can either go to state 9 and take the wolf across, or he can go to state 6 and take the sheep across. From there, both routes have just one state they can go to until they converge together on state 5. And finally, they end up in the desired state. What we drew here is a simple graph, and it clearly shows us that there are two solutions to our puzzle. Now, it's important to note that this is not a directed graph, even though I used arrows to connect two nodes together. We can always move back and forth between states.
So he goes into the details of Leonhard Euler and graph theory and Königsberg and stuff like that, which is really interesting in my opinion. But that is not the purpose. The purpose is, again, showing that a real life, no, not that is a real life situation. You have buy a wolf, a sheep, and a thing of cabbage. But you can take a problem like that and you can basically turn it into what is known as graph theory. We took Königsberg the other day, last week. We took Königsberg and we were able to turn it into this idea of graph theory and eventually explore the concepts of Euler paths and circuits. I tried getting something ready for you guys. I actually printed out a map, a Google map of Settlers Landing in Barnegat. And I was gonna figure out, okay, how can I convert Settlers Landing into this concept of a graph theory? It's going to take me a little bit more time to figure that out, just because I needed to kind of mess with that map a little bit and figure out exactly where am I going to put these nodes, because I was thinking about trash trucks. And if a trash truck is going to travel throughout Barnegat, I have to think about the concept of, they only pick up the garbage on one side of the street and then the other side of the street. And it was a little bit too difficult for what I wanted to do, but so I left it alone. The last thing I want to show you is a little bit of a game. I mentioned the 5-pointed star. Check this out. There's a little game that you can play. Points versus counts. And I'll put that as Q. 5 points. 1, 2, 3, 4, 5. Give me a number that's not 1 or 5. 3. Okay. You just pick 3. That's fine. I'll start here. If I start here, I'm going to count over 1, 2, 3. Make a connection. Then from where I am, I'm going to count 3 again. 1, 2, 3. Then I'm going to count 3 again. 1, 2, 3. Then I'm going to count 3 again. 1, 2, 3. Count 3 again. 1, 2, 3. And then I got the star. Now, you know how to do that by freehand. You said the elementary school is just knock that thing out, right? But check this out. Make 6 points. It's just a fun little game that you can play with, like this idea of graph theory, with creating images and seeing what kind of thing can pop up. Now, the reason why I told you not to pick 1 or 5 was because if you did pick 1 or 5, I would literally be drawing a pentagon. I didn't want to draw a pentagon. So I can't pick 1 or 6. Pick a number that's not 1 or 6. 2, all right. Because if you pick 1 or 6, you'll end up with a hexagon. Start anywhere you want. I'll start here. Count 2. 1, 2, connect. 1, 2, connect. 1, 2, connect. Oh, I'm in a loop. All right, let me go to the other one. 1, 2, connect. 1, 2, connect. 1, 2, connect. 6-pointed star. You can make any pointed star that you want. The more interesting stars are the ones where you have a prime number as the number of points. So I'm going to do 7 right here. Pick a number that's not 1 or 7. All right, let's pick 5. 1, 2, 3, 4, 5, 6, 7. I was just trying to get 7 points kind of in a circle to see what kind of thing this would make. I'll start anywhere I like, and I'll start counting clockwise. From this point, I go 1, 2, 3, 4, 5, connect. I'll start where I ended up. 1, 2, 3, 4, 5, connect. 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 7-pointed star. There's a lot of number theory that goes into this. Unbelievable amounts of number theory. The reason why I suggested starting with a prime number is because with a prime number, you can get a unique shape depending on what Q value you pick. Whereas if you ended up with something like 6, you picked, what did you pick? You picked 3, I think? Yeah, 6 is divisible by 3, which is why we ended up with 2 unique shapes overlapping each other. Whereas with this one, it was literally one continuous star that we drew, just like the 5-pointed star. It's insane. Like it's like a little kid's game, but applying like high levels of graph theory and number theory just to behind. I don't know. It just blows my mind sometimes. Anyway, I won't see you guys until the 12th. Almost 2 weeks. Insane. Hopefully, I don't know. Is it going to rain all spring break? I don't know. I haven't looked at the weather yet. But we'll see what happens. Anyway, I'm going to sign off on the live stream. We got about a minute left in class. If you haven't left a comment, please leave a comment. I've already seen the couple that have left a comment. And just so the two of you know, in the Google Classroom stream, I posted a comment because I thought the chat wasn't working, where I asked people to leave a comment. Clearly, you two don't have to do that because I clearly see that you're here. So just giving you that heads up. Don't worry about that. That's for people who were supposed to be, but weren't, and now we're absent, except for the couple of comments that I see here. Anyway, I'm going to sign off. Click and click.